All right, here we go. All right.
It's not in our book.
I said it 4 times, Braxton. This is not in your book. I
I
said it 4 times, Braxton. I got it on video right here. 4 times. All right. The scientific study of motion is called mechanics, or the study of mechanical energy. Motion can be a straight line or in an arc. If something is moving around an axis, it is said to have circular motion. Gravity plays a large role on how things move on Earth. Mechanical energy is one of the most visible types of energy. Other types of energy includes chemical, electrical, light, nuclear, and thermal, which is heat. Okay? Unlike chemical, nuclear, and electrical energy, which takes place on a microscopic and atomic level, mechanical energy is easily seen, measured, and tested. You can see things and people moving around you all the time. Okay? Like all forms of energy from a scientific viewpoint, mechanical energy is the ability to perform work. And performing work can get, when we get into what is work, that's a fun one too. Okay? You perform work when you move something. You use mechanical energy in countless ways. You use it to brush your teeth, comb your hair. You use mechanical energy to ride a bike, mow the lawn. Mechanical energy swings a bat to hit a home run. It allows you to slide down a snowy hill. All that's mechanical energy. People have also learned to build machines that allows them to do much more work than they could without machines. Using a machine to increase your ability to do work is called mechanical advantage. Mechanical advantage allows people to build bridges, skyscrapers, aircraft carriers, airplanes, things of that nature. Okay? Now, physical laws. All objects in the universe move accordingly to specific laws. Okay? For example, all objects obeys the law of gravity. They don't have a choice. Everything on Earth is pulled towards the center of the Earth. And we will be studying more of the specific types of physical laws that govern movements as objects, okay? These physical laws are different from other types of laws, okay? Number one, physical laws were not invented by man. They're only described by man. Man has realized that they exist, but man did not invent physical laws, okay? That is nature. Physical laws cannot be broken or changed. Man cannot override physical laws. Okay? Physical laws applies throughout the entire universe. So it's not just in this classroom, it's throughout the entire universe. And physical laws were set in place by God. That's where they came from. Okay, so man cannot override them.
Unless God says it's okay.
God is not going to allow man to override nature, I can assure you. He hasn't ever done that. He's not going to let it happen now. All right, so, but yes, if he did make that decision, that would be the only time you can do it. You're absolutely correct. Okay, so describing and measuring motion. Okay, you're on page 6 in your brand new book. Your brand new old book, yeah. Okay. New to you. How's that? Okay. All right. So this is pretty simple. Again, it can get complicated, or not complicated. It can get confusing if you're not careful. As we get a little deeper into this, none of it is incredibly hard, but it's kind of like if you start missing out on the first 2 steps and you try to pick up with step 6 and 7 on something, you're going to be a little bit lost. It don't mean you can't recover, but you're going to be a little bit lost if you're not careful. Okay? Yes, Julia.
What's the project that we do on this?
Don't worry about the project. Okay? Project's a long way. That big project's a long ways off. Okay? How do you know if you're moving? If you've ever traveled on a train, you know you cannot always tell if you're in motion. Looking at building outside the window helps you decide, although the building seems to be moving to move past the train. It's you and the train that are moving, okay? So, you know, as you go down the road or you're on a train, you look out and a house goes by, okay? Yeah, it looks like the house is moving, you know, going the opposite way. Of course, we all know it's not. The house is sitting still.
It's like
You're
the
the
sun.
one
When you look at
moving,
the sun, it
okay?
looks like a-
So it's a reference point, okay? However, sometimes you see another train that appears to be moving. And is that train really moving, or is your train moving, and how can you tell, okay? So this is where we get into describing motion.
Or are they both?
Deciding if an object is moving isn't as easy as you might think. Remember, this is scientific here, okay? So common sense sometimes goes out the window because science describes things a little bit differently, okay? For example, you're probably sitting in a chair as you read this book. Are you moving? Well, parts of you probably are. Your eyes blinking, your chest is going up and down, but you'll probably say you're not moving. So an object is in motion if its distance from another object is changing. Because your distance from your chair is not changing, you could say you are not in motion. So if I stood here and I'm swaying back and forth as I'm talking, you would say that I'm moving, right? Scientifically, I'm not moving because I'm not getting any further away from Rihanna.
Well, you are
Okay, so
getting
therefore,
further
I'm not
away.
moving. Okay, scientifically, I am not in motion. I am not moving. I'm moving, but I'm not in motion. Okay, that's a
Wait,
better
if
way
you
to
were
say it.
eating
Okay.
like this, would you?
No, I'm not getting further away from her. I'm standing here.
So you're at a
I am
fixed
not getting further away from her. Okay? Okay? Now, a reference point. To decide if you are moving, you use your chair as a reference point. Excuse me. I swallowed wrong. A reference point is a place or object used for comparison to determine if something is in motion. An object is in motion if it changes position related to a reference point. Okay? Objects that we call stationary, such as a tree, a sign, or a building, makes good reference points. For the point of view of a train passenger, such objects are not in motion. So if the passenger in a is moving related to a tree, he can conclude that the train is indeed in motion, okay? Because that tree, he's pretty sure that tree is not running down the track. It's staying stationary, right? You probably know what happens if your reference point is moving. Have you ever been on a bus or in a car or something, and the car beside you starts to back up or move, and all of a sudden you're like, oh, are we moving? And no, it's not you, it's the guy beside you, but because that reference point is moving, it kind of throws you off just momentarily until you realize, oh, okay. Okay? If you're moving, are you moving as you read this book? It's on page 8. Okay? The answer to that question depends on your reference point. When your chair is your reference point, you may not be moving. But if you choose another reference point, you may be moving. Okay? If you're picking the sun as your reference point, even though you're sitting in your chair, technically you're moving. Because the earth is moving, and you are on the earth, so therefore you would be moving because we're rotating around the sun. We're orbiting the sun, so therefore we would be moving. You see, not hard, but it can get confusing, okay? So
it depends on your reference.
it depends on your reference points on whether or not you're moving.
Reference
Okay?
point where your posts are without the eagle, then I wouldn't be moving. But if it were,
If there's anything in this room and you're sitting still, unless you're getting further away from it or closer to it, technically, scientifically, you're not in motion.
I'm moving if I
Okay.
do this.
Oh. The book, you put the book in motion, but then you bring it up. Okay?
But it's going
So.
farther into the
So, measuring distance. You can measure the unit, you can use units of measurement to describe motion precisely, okay? You measure in units or standard quantities of measurement. All of the time we do that, okay? For example, you might measure for 1 cup of milk. You might go out and run 2 miles at cross-country practice after school. You might buy 3 pounds of fruit at the store. So cups, miles, and pounds are all units of measurement. Okay? Scientists all over the world use the same system of measurement so that they can communicate clearly. This system of measurement is called the International System of Units. Or in France, it's just called the System International, SI. Okay? So scientists uses the SI unit of measurement. Okay? All scientists throughout the world. When describing motion, scientists uses the SI unit to describe the distance an object moves. When you measure distance, you measure length. So the SI unit of a length is the meter. Okay, we're about the only civilized country that is still on the standard measurement forms. We studied using the standard instead of using the metric system. Okay. When you measure distance, you measure length. So the SI unit of length is the meter. A meter is a little bit longer than a yard. An Olympic-sized swimming pool is about 50 meters long. A football field is about 91 meters long. Now the length of an object smaller than a meter is measured in a unit called the centimeter. The prefix centi means 100. A centimeter is 100th of a meter. So there is 100 centimeters in a meter. Okay? The system is actually set up on tens. It's actually a fairly easy system to figure out.
What about Miller?
The wingspan of the butterfly shown up in the picture there on page 9 would be measured in centimeters. Okay? Now, if it's too small for centimeters, then you have millimeters. Okay? And that is used, The prefix milli means 1,000. So there are 1,000 millimeters in a meter. So distance too long to be measured or too big to be measured by meters or measured in kilometers. Okay? And the kilo means 1,000. So there is 1,000 meters in a kilometer. So scientists uses the SI unit to describe quantities other than length. Okay, and we talk about that a little bit more later on also. But the converting the units, you're going to be doing some math in this unit. Primarily is multiplying and dividing what you're going to be doing. Okay, but you have to follow the formula to know when to do what. Okay, so you're going to be introduced to various formulas and things like that. And as long as you plug in the numbers, you'll be able to do it. Okay. Calculating speed. This is kind of a long introductory here, okay? A measurement of distance can tell how far an object travels. A cyclist, for example, might travel 30 kilometers, and an ant might travel 2 centimeters. If you know the distance an object travels in a certain amount of time, you can then calculate the speed of that object. But you got to know how far they went and how long it took them in order to figure out the speed. Okay? Because speed, the formula for speed is speed equals distance over time, which means time is divided into the distance. Okay? To calculate the speed of an object, divide the distance and the object traveled by the amount of time it takes to travel that distance. The speed equation consists of a unit of distance divided by the unit of time. Okay? If you measure distance in meters and times in second, you read speed in meters per second, or ms. Okay? The m/s is meters. The slash is basically per, so it's meters per second. Okay? If you measure distance in kilometers and time in hours, then you would express it kilometers per hour, or km/h, kilometers per hour. Okay? Now the average speed, this is pretty simple stuff. The speed, most objects is not constant. A cyclist in a race, okay, for example, they change their speed many times during the race. Okay, they might ride at a constant speed along flat ground, but they move more slowly as they climb hills. Then they might go faster as they're coming off of a hill, coming down that hill. Okay. They might have to occasionally stop. Maybe something goes wrong with the bike and they've got to stop and work on that bike for a few minutes. All that is still incorporated into the time. Okay, they don't stop the clock because he has to adjust something. Okay, that time keeps going. So although a cyclist does not have a constant speed, the cyclist does have an average speed throughout the race. And to calculate the average speed, divide the total distance traveled by the total time. And it shows you here, the guy he rode for 2 hours and he covered 32 kilometers. And then he rode another hour and he covered 13 kilometers. So you would add the 32 and the 13 kilometers, and he covered a distance of 45 kilometers. And he did that in 2 hours plus another hour, so 3 hours. So the formula to figure that out would be 45 kilometers with a line, 3 hours, which means 3 divided into 45. So you would divide the 3 into 45, and you would come up with 15 kilometers per
round down?
hour. No, you don't round down.
Oh, like if it doesn't go
You don't round down.
Okay.
You don't round down. It's precise. Gotta be precise. Especially in like talking about a bicycle race. Sometimes these things are decided. I mean, think about the Olympics when the swimmers. These things are decided sometimes by 100th of a second between, first and second place. I mean, they're that close. So no, they do not round down. Okay.
Sometimes there's like it's like 1,000.
Sometimes. They're very
What
close.
if they're
Sometimes.
the exact?
Okay. Now, instantaneous speed, we're not going to worry about that so much. Calculating the average speed, of a cyclist during a race is important. However, it is useful to know the cyclist's instantaneous speed. Instantaneous speed is the rate at which an object is moving at a given instance in time. Okay? Again, we're not going to get into that quite as heavy. Okay? That's for a little bit later on. Okay? Now, we have talked about velocity before. Okay? Knowing the speed at which something travels does not tell you everything about its motion. Okay? If you're sitting at home and you turn on the radio or the TV and it says there's a severe thunderstorm and it's moving 25 kilometers an hour, that really doesn't tell you anything other than there's a thunderstorm somewhere out there in the viewing area, but you don't know where it's at or where it's moving. Okay? So if he comes on now and he says it's 25, you got a thunderstorm that's moving 25 kilometers per hour east, and you live up in the western or the northern part of the county, you probably are safe. It's probably not coming in your area, right? But because you have to know, and that's what velocity is. Velocity is speed and direction, okay? It's got to be 25 miles per hour west, not just 25 miles per hour, okay? So velocity is 25 miles per hour with a direction added to it, okay? Speed is just the number thrown out. Yes, sir?
So instantaneous speed, so let's say you cycled, let's say a mile, in, let's say, an hour, is not reasonable. It's just an example.
Well, but again, the instantaneous speed is how fast are you going at any particular time.
Oh.
Okay, because what we're saying is when you drive, if you ride 20 kilometers in an hour's time, you did not go 20, you didn't go that fast the entire
Yeah, so
time.
if at like you did a 2-hour race and at 1 hour 54 minutes, if your speed was 22 miles, then that would be a speed. So it's like your speed at a given moment.
At any given moment, yes, that's it. Yes.
So, would it be different, like if it were, let's say,
Well, it changes depending on distance and
Well, I
time.
was gonna say is like if you had two horses, one smaller horse and one bigger horse, one's gonna have a bigger stride and it's gonna look
Sure,
slower,
all that would come into play,
Faster.
absolutely. Sure, all that would come into play. All that, that's why racing bikes usually does not have the little 16-inch wheels on them. They've got the big ones, so, yeah, it definitely covers more distance with less work, okay? All right. So when you know both the speed and the direction of an object's motion, now you know the velocity of that object, okay? And at times, describing the velocity of a moving object can be very important. For example, take an air traffic controller. He must keep close track of the velocity of an aircraft under their control. These velocities continue changing as airplanes move overhead, they're on the runway, and an error, of course, can create a collision if they're not careful. So they have to be very, very much on top of it. Leo and Brady, y'all really do need to be paying attention because when you failed this, I got it on tape that you did not. You're my witness, by the way. You might be called before you serve on the jury.
Wait, I thought they were going to come back after first quarter.
Apparently not. Okay, they opted not to come back second quarter, which is fine. That's okay. Okay. How many of you ever seen like the Blue Angels?
Me.
Yeah. I mean, it don't have to be live and in person. I'm talking even on TV. How many of you know what the Blue Angels are? Okay. They're the Air Force. They fly. They're stunt pilots. They fly very close formation. Okay. They have to be very precise in velocity here. Okay, they got to be very precise in their velocity. One era, because they're flying within just a few feet of each other in jets, going really, really fast and making maneuvers. So they have to be very precise. Their velocity has to be, they have to be dead on at all times. Yes.
So that means if their velocity changes, they also need to change where
Yes,
they're
every time
flying.
one of them changes, the other one has to change also. Absolutely, that's what that means.
Yeah, so it's like,
Otherwise, they would crash.
yeah, so if they had to take a turn and their velocity changed, then
Yes. If one changes, they all change. Yes, Morgan.
About a year ago, my grandfather passed away, and he would give money to this association that would give free homes to wives of veterans that have passed away. So my mom and her two brothers went to this to the association and gave money to help this a woman and her daughter get a house, and that I think it was that group or it might have been another group flew over like a celebration.
Oh, cool. Very good. I'm glad you got to see it
Yeah,
at a celebration.
it's kind of like the Blue Angels. What is the Blue Angels? If they're flying and one of them turns a little, they're on there.
Yes.
Yeah.
Talking about if they're not precise, if their velocity and everything is not
If they're not
dead on, they could cause a
Leo,
crash.
if they're not perfectly level, they could hit the other
Yes,
person's
I think
plane.
we have covered that now. Okay. All right.
Well, maybe not.
Drafting motion. We're not going to get into this hot and heavy. You guys that are in free algebra, you might talk about sloping this year. I don't know if you get into that in pre-algebra or
No,
not.
we're getting into
You
that.
definitely will get into it in algebra when you get there. All of you will when you hit algebra. And we're going to talk a little bit about what sloping is. I do not expect you to be working any problems that deals with sloping right now, because this is, even though we're getting into a little bit of physics, we're not getting into the heavy-duty math portion of it. Okay? So you can show the motion of an object on a line graph. You see that up there at the top of the page on page 14. And you notice you got the distance in meters going vertically. You got time in minutes going horizontally. And what you do is you plot it, and right here it shows a guy, like the first point is 2 minutes, and he covered 400 meters, okay? And the next point is 4 minutes in, and he's covered 800 meters. And then he covered another 400 meters. And so in 6 minutes, he covered 1,200 meters, okay? So to figure out what he was averaging per 200 meters, or 400 meters, you have to do the math, and it's 2 minutes, okay? Because 6 would go into 1,200 meters 2 times. So he's covering it in 2 minutes, okay? Yes, Mr.
Can I
Wood?
use that?
Yes. Okay? Now, where the slope comes in, the steepness of the line on the graph there is called the slope, okay? And the slope tells you how fast one variable changes in relation to the other variable in the graph. And this was a very simple one, okay? They can get a lot more complicated, obviously. You're going to get into the rise and figuring all that stuff out. But again, we're not worrying about doing that in this class, okay? But just to let you know, it's something to look forward to. It is interesting when you get into it. It's really quite interesting to get into. All right, we're going to hand out homework now. Hope y'all enjoyed that a little bit.